This is problem 3-123.m. It's on page 172. A round shaft has two grooves in which rings are placed to retain a gear in position as shown in figure P3-123. If the shaft is subjected to an axial tensile force of 36 kilonewtons, compute the maximum tensile stress in the shaft. Now the point of this exercise is to realize that that groove is going to cause stress concentration. And so the maximum stress is going to be higher than the nominal. Alright, so in order to deal with this, we'll have to have a stress concentration factor, which we'll get from correlations, essentially, measurements of materials made in the shape. So page 724 is where we want to go. Page 724 has stress concentration factors for this very geometry, for a groove with a given radius. You'll notice on the x-axis, the radius of the groove divided by the diameter at the groove of the shaft is the x-axis, and then the ratio of the larger diameter of the shaft to the groove diameter of the shaft is the curve. It tells us which curve we're on. But you'll notice we'll run into a problem with this. Let's notice another thing. The nominal stress is calculated at the lower groove. You should go to page 724 and see what I'm talking about, because then the symbols I write down here will make a lot more sense. Anyway, to calculate the stress, the nominal stress is calculated based on the smaller diameter, the diameter in the root of the groove, basically. And so that's just force over area, but there's a note at the bottom that says that that is calculated as force over pi over 4 diameter of the groove squared. So in our particular case, this is a 75 millimeter dimension. So if we plug in the numbers, inverting the 4 to put it in the numerator, the force applied is 36,000 newtons, and the diameter of the groove is 75 millimeters. I'll just leave it as millimeters because then we'll get gigapascals. It has to be squared. Plug all this in your calculator and you'll find that this is about 8.1487 is how many decimal places I took, times 10 to the negative third gigapascals. So there's the stress in the nominal stress in the shaft. So it's based on that smaller groove diameter. Now, to determine the stress concentration, because what we're really going to do is say, well, the maximum is the stress concentration factor, which we read off the y-axis on this figure, multiplied by the nominal stress. Well, we've got the nominal stress. Now we need the stress concentration factor. To get that, we'll use r over, and let's see, x-axis is dg, and so r in this case is 3 millimeters divided by 75, which comes out to 0.04. Notice these both have units of millimeters, but I didn't write them because they cancel. The 0.04 is dimensionless. Now it already looks bad because at 0.04 on the x-axis, you'll notice we kind of hope we're on the 1.05 curve, otherwise we're off the graph. Well, let's find out which curve we're on. The diameter of the shaft divided by the diameter of the groove is 85 millimeters over 75 millimeters. I just thought I should double check that. For some reason 80 is sticking in my mind. Let me run back to the problem statement quickly. Let's see. Yeah, sure enough, it's an 85 millimeter outside diameter. The inside diameter at the bottom of the groove is 75 millimeters, so that's fine. This is correct. That means that ratio is about 1.13. It's also non-dimensional. Now you notice we have a problem because the curves that are listed for this ratio are 1.05, 1.1, and 1.2. So our curve, the one we want, 1.13, is between the curve for 1.1 and 1.2. It's closer to the curve for 1.1. However, in this graph, the highest stress concentration factor we have for even the 1.1 curve is at an x-axis value of 0.06. But our x-axis value is 0.04, so we're to the left of this. The best that I could do was extrapolate that curve up And that's not a very good thing to do, but that was the best that I could do because it's off the chart. And so here's my best guesstimate. Stress concentration factor is about 3. If you put down a stress concentration factor of 4, would that be wrong? No, you're guessing 2, right? So what about a value of 10? Well, 10 would probably be excessive, but somewhere in this range is reasonable. So that's my best guesstimate, let's call it. Then the maximum stress would be 3 times the nominal stress, the 8.1487 E negative 3 gigapascals. Plug all that in your calculator, convert it, and you'll get 24.5 megapascals or so. Okay, so is this right? Is that 0.5 valid? Probably not. Would 30 megapascals be valid? Sure. It's just as good as this. So we're guessing because, or at least I'm guessing, because the stress concentration factor is off the chart. We don't have data for it.